As the story goes, at some point in 1908, a Romanian math professor, Gheorghe Țițeica, was passing time by drawing circles with a 5-lei coin. What Titeica discovered is a simple construction of 3 equally sized circles passing through a single point. When drawn like this, there are 3 other points where the circles intersect with each other. The meat of this theorem is that if we draw a 4th circle through these 3 points, it will have the same size as the circles we started with. Simple, elegant, neat. How did Euclid and his disciples, or anyone after him for that matter, miss this simple theorem? After all, coins have been around for a good while before 1908. The answer was best put by Roger Arthur Johnson, who was an American geometer, who also discovered the same theorem as Titeica, but 8 years later, in 1916. He published it in the American Mathematical Monthly, but wasn't aware of Titeica's result, as it was only published in Romanian. After proving the theorem, Johnson wrote, "Singularly enough, this remarkable theorem appears to be new. The figure is so simple that it seems almost out of question that the fact can have escaped detection. Even if geometers have overlooked it, someone must have noticed it in casually drawing circles. But if this were the case, it seems like a theorem of sufficient interest to receive some prominence in the literature, and therefore ought to be well known. It is hoped that if any reader recognizes the theorem, or knows where it has already been given, he will report the same." Well, nobody reported, and so the theorem is also known as the Johnson Circles theorem, alongside the names of Titeica's theorem and the 5-lei coin problem. Now, let's prove it. I'll show 2 visual proofs. Both can be made rigorous, but I'm not here for that. I'm here for making pretty mathematical pictures move on the screen, so here's the first one. The 3 points where the circles intersect can be used to form a triangle. Then the 4th circle is a circumcircle of this triangle. That is a circle that passes through its 3 vertices. But we can also form another triangle by joining the centers of the circles. A circumcircle of this triangle is for sure the same as our original circles, since its radius coincides with each of the other circles. Now, if we can show that the 2 triangles are the same, just rotated differently, we would prove that their circumcircles are the same. I'll let the animation speak for itself. Quite neat, right? Here's a little more out-of-the-box proof. Since we have 3 circles of equal radii, maybe we better show that in our picture. Drawing the line from each circle's center to a point of intersection, we get this shape. Does it remind you of anything? Well, it looks like a 2D projection of a cube to me. But quite a special one, since each line segment of this projection has the same length. What we are missing are the 3 lines that would give depth to our cube. Drawing these in, we can see that they are also of the same length, and meet at a single point. So a circle centered at this point, and passing through the ends of the 3 newly added lines, will have the same radius as our original circle. And this concludes the proof, as well as the video. Thanks for watching, see you in the next one.